In this video, I'm going to go through an example of how we use the second order run cutter method, also known as RK2, to solve an initial value problem. And our initial value problem, this is from example 2.2 in the notes. It's going to be y dash, or derivative of y, is equal to sine squared t times y. The domain is t goes from 0 to 5, and our initial value of y is going to be 1, and I'm going to be using h equals 0.5 as a step length in this example. Okay, so the RK2 method, okay, I'll write that down here. So we've got yn is equal to yn plus h over 2 times the sum k1 plus k2. Our first stage value, as with all explicit run cutter methods, is f of tn yn, and our second stage value is f of tn plus h and yn plus h times k1. Okay, so what this is our RK2 method. Okay, and this is what we're going to use to solve or calculate the first, say, 2 steps of the solution for this initial value problem. Okay, for step 1, what we have is, we know that t0 is the lower bound of t, which is 0, and we also know that y0 is 1. So what we do is we calculate our first step, which is k1. Now what we're going to do is we're going to use the function f of ty. So f of ty is sine squared t times y. So we have sine squared times t, which in our case t is 0, multiplied by y0, which is 1. So that just gives us k1 is equal to 0. K2, we've got sine squared. Now instead of t, we put in t plus h. Now t plus h is going to be 0 plus h is 0.5. Don't forget the decimal point. And we're also going to put in yn plus h times k1. So yn is y0, which is 1. So it's 1 plus h is 0.5 times k1. Now k1 just happened to be 0 in this case. Okay, so if we do those sums, we get 0.2298. Okay, obviously I've done this before, I haven't just calculated that in my head, in case you're wondering. Okay, so if I update the solution, so now we're going to use this to update the solution. So we have yn, which is 1, which comes from here, plus our value of h divided by 2, multiplied by k1, which was 0, plus k2, which was 0.2298. Okay, and if you do that sum, you get 0.0575. So that's our value of y in 1 step time, and we could also update our value for t, and all we do is we simply add h to our current value of t to get 0.5. So y1 and t1 here, t1 is 0.5, y1 is the solution of y at t1. Okay, so that was step 1. Step 2, do exactly the same, but this time we have new values for t and y. So in this point, k1 is going to be equal to sine squared t, which is now 0.5, times y1, which is 1.0575. Okay, and calculate that, and you get 0.2431. For k2, okay, same as before up here, we have sine squared. This time it is tn plus h, so we'll have 0.5 plus our h of 0.5. Okay, and that's multiplied by y1, which is 0.0575. So just to remind you, but this comes from this function here. So instead of t, we have t plus h, which is 0.5 plus 0.5. Instead of y, oh sorry, not instead of y, I made a slight mistake there, Okay, so we had instead of y, I should have had yn plus our value of h, which is 0.5, multiplied by k1, which is 0.2431. Okay, I almost made a mistake there. Okay, so if we calculate that, we get 1.32969. Okay, so now we've got K1 and K2. Again, we can now calculate Y2. So Y2 is going to be equal to Y1, which was 1.0575 plus our H, which is 0.5 over 2, multiplied by the sum of K1 plus K2. Just realised I've made a mistake here, so I'm just going to so I've copied down the wrong value for K2. Okay, so K2 should have been 0.8348. That also goes in here. Okay, so this is actually 1.3269. I just copied down the wrong number. Okay, and also we can calculate T2, which is going to be equal to T1 plus H, which gives T as being 0. Okay, so I could go on. If I'm using a step length of H as 0.5 over domain 0 to 5, it requires 10 steps. I'm not going to go through all 10 steps at risk of boring you, but you can see the first 2 steps are here, and we just continue as we've done here.